There we go. Okay, so week 6, I can't believe it's already week 6. We are more than halfway through the term. We need to finish up section 5, and then we are done with chapter 6. I decided we're not going to do the next section, which is more physics stuff, moments and centers of mass. It's cool stuff, but I think we need to move on to other techniques. So we're going to finish up work, pressure, and force with calculus today. There's a quiz for section 5 here that you should take a look at. We'll do a couple similar problems to that today. Under exam 2, there's no exam posted there because you're going to have a written exam soon, but I did post a practice exam earlier that I'll show you. And the big things here are kind of similar to the last exam. It's going to be on paper, no notes, text, apps, or websites. I'll give you a sheet of some formulas that you can use along with the test, but you can't use things like Wolfram Alpha Mathways or something similar for the in-class part. I am going to give a couple of take-home questions, kind of like the quizzes, that you're just going to go off on your own and do and bring them back the next class. So the test will be in 2 parts: in-class, few questions; take-home, couple questions. The test will be similar to the sample test I posted over here under sample exams. I decided, I think we talked about this in class one day, I don't like the practice tests in my math lab. I don't like the way they work, so I'm deleting all of those from the course. There won't be any more of those. So to study for the test, you should take a look at your homework, take a look at your notes, and then take a look at this sample test here. And these are the kind of questions that you'll see on the test. So 6.1, you have a cross-sectional solid that we integrate through. We did a couple of those. And then there's our volumes that you can rotate, a few different versions of that. Then we did arc length. And remember in class, I talked about the idea of a cable hanging, gravity pulling down. We get a shape called a catenary, which is a hyperbolic cosine. Now, all we need to know is that this formula right here is what makes a hyperbolic cosine, and we can find an antiderivative for e to something pretty easily. So it turns out it's not that bad. We'll talk more about hyperbolic cosines in chapter 7. And then we have surfaces that we've been playing around with. On the test, I try to pick problems for which an antiderivative exists. So there should be a way to do it. In desperation, you can always get an approximation based on your integral. But in all of these problems, unless I say, just give me an approximation, there should be an antiderivative that you should be able to find. And the main types of physics problems I'm concerned about are the idea of work and pumping, which is work, pulling water out of some kind of container. But we'll also take a look at pressure also today. All right. And your in-class test will be shorter than this slightly because you couldn't do, I don't think it's possible to do all these in an hour, even for me. And again, each problem here is relatively complicated, which is why I like to give you a part take home so you can do it when you're not under pressure. All right, so that will be on Wednesday. So with regard to that, I also posted a new schedule. Where's our calendar? I updated the calendar here showing where we actually are on the course. The other one had us a day or two behind. So I talked about 6.5 a little last week. We're going to do some problems today. Tomorrow's a review day. Exam is on Wednesday. And then we're going to pick up with chapter 7. And I cut a couple sections out. I took out 7.2 and 7.4. We're only going to do 7.1 and 7.3. And then we're going to try to do all of chapter 8. And we have a little bit of wiggle room here at the end. So I think this is doable, as long as we don't have any more snow days, which is, I have no idea if it's likely or unlikely. Seemed likely based on history. Have we had a full week yet this quarter? I know the public school hasn't. I guess we did, but it was sketchy last week, wasn't it? All right, let's do some math. So, first problem we'll look at is a conical tank. Let me orient my board. Please tell me sound is working. Yes, it is. Good. Hello. Come on. Let's hope this works today. So, let's take a tank that's shaped like a cone with a top radius here of 4 and a complete depth here of 12. And what we want to do is, let's say it's filled with water all the way up to the top. Oops, I wanted red. We want to pump out the top 8 feet. And what we want to know is how much work is that? And so just a reminder about what work means. If I, just a simpler example, if there's a big box sitting on the ground and it's got some weight and I want to move it, right? Maybe I'll just try to slide it across the ground. So I'm going to grab that box and I'm going to try and push it along. Okay. Now, if it's heavy, am I going to have to work at it to push it? Right. Yeah, I'm going to have to work at it to push it. There's going to be friction that's making it drag, and I'm going to have to push and use my energy to do so. So I have to use up energy, and that's what we call work. So this box is resisting me because of its weight and the friction with the floor. Okay, and work is defined as force times distance. Now, if we consider the floor to be relatively uniform all the way through, then that means there's going to be a constant force resisting me as I push it, and that's a pretty straightforward problem. All we have to do is find a way to calculate what that resistive force is and multiply it by the distance that we traveled there. No calculus involved there. It's just some measurements. However, in this case right here, I'm going to have different volumes of water moving around. Right, so the volume of that rectangle is a little bigger than the ones below it and a little smaller than the ones above it. And then each of those little rectangles is going to be moved a different distance. Okay, so distance is varying, which I expect, but because I'm going to have different volumes, I'm going to have a variable force. And that's why we need calculus to do this particular problem. Okay, with the box problem, that's a fixed force, and that's just arithmetic and experience. Because this is a variable force, it's going to require calculus. Okay. Due to the shape of the container. If it was just a cylinder, no calculus needed. That one's pretty straightforward, but this one is not. So some things I need to know. What's resisting me here as I'm pumping this? Well, the weight of the water. And where does weight come from? Anybody know? From gravity, right? So any particular thing, if it's relatively uniform in density, is going to have a weight volume constant. Okay, so for water, it's approximately 62.4 pounds for every cubic foot is the weight density of water. And our book has a little table talking about, I think our book has a table. Let me double check. Let's see, where'd it go? Yeah, right here. Let's blow that sucker up and scroll down. Oh, too far, darn it. Get back here. I don't know, I messed it all up. Oh. All right, this is not going well. Come on. There we go, almost there. And you can look these up online. Usually there's websites or physics, oops, too far, textbooks that have them. So here's the weight density of different kinds of fluids that we can pump. And in the homework, you're going to be asked about different ones of these. Gasoline's a little lighter than water. Mercury is wicked heavy. Milk's a little heavier. Molasses is really heavy. Oil's heavier. Obviously, seawater with salt is a little bit heavier, given a cubic foot of it. Okay. So those are going to be needed whenever we do problems like this. Okay, so let's go about doing it again. So what we need to do is sketch out our cylinder so we can try and work with this. And what I'm going to do is I'm going to kind of reverse this. I'm going to say y going down is positive, so that's going to be 12 down there. And I'm going to put x equals 4 over here. And so a cross section of half of my cylinder, sorry, my conical tank is going to look something like that. So this is the x-axis up here, and that's x equals 0. And we're going to take this down to y equals 8. What we need to do is thinking about that cone, draw that over here. So the resulting cone looks something like this. We need to figure out what's going on with a chunk of this water. Let's call that delta volume. So we're going to take a chunk of that water, and then we're going to move that water up to the surface, is what our goal is. So say we're just pumping it to the top, and then it can go wherever it wants after that. So we want to pump it up there. So just some things to consider here. The distance that I'm pumping it up, according to the axes I chose here, my direction being down, that distance up is just the y value. To get the volume of this disk right here, well, I know it's delta y thick. I need to figure out what is its radius here so I can get its cross-sectional area. To do that, say that's at some instant right here, I need to know the length of that line. That's going to be my radius. That's an x distance, right? Yeah, so my radius is an x distance, and it's going to be some function of y, the height. Every height's going to be slightly different. Now, I'm used to thinking of things as y as a function of x, but we could flip it and go the other way, right? So in this case, what do we have? We have an x-intercept instead of a y-intercept of 4. So we're going to enter something like x equals my plus b. That's what we're going to calculate. So 4 is the x-intercept instead of the y-intercept. And the slope, instead of rise over run, is run over rise. Okay. So let's see. My run over rise, and it might help to think about this flipped. So this on a normal y-axis is what we're working with, right? And so my run here would be 4. Like, let's say I want to get from, actually, let's go from, I don't know, this point here to that point here, so 1 to 2. So I could say my run is 4, and then my rise is what? Negative 12. It's going to be a negative 12. So I'm going to have negative 4/12 y plus 4. So just double check. If y is 0 here, what's x? 4. And if y is 12, then we get 0 for x. So that works out. So that gives me the right points. So this right here, cleaned up, is my radius. So what's that? Negative 4/12 is what? Negative 1/3. So my radius here of my cross-sectional circle is negative 1/3 y plus 4. So that means the area on top there, let's call it delta area, is going to be pi times that radius squared. So getting to my delta volume here, the volume here is going to be the cross-sectional area of that circle, which we have right there, times its thickness. Okay, so that gives me something that's two-dimensional times something that's one-dimensional, which gives me a three-dimensional volume. Okay, so it's going to be pi times that negative 1/3, oops, negative, that's not coming out so hot, negative 1/3 y plus 4 squared dy. So that's the volume. If I take the volume of that thing times the weight density, that's going to give me the weight, which is the force. Okay. So my chunk of weight is going to be equal to the 62.4 pounds per cubic foot times that amount of cubic feet. Pi negative 1/3 y plus 4 squared dy. All right, so we're slowly building up what we need here to make our integral. We want to calculate work. So new page. Oops, wrong way. Work for a variable force is equal to the integral of that variable force times the distance of whatever you're moving that stuff. In this case, we're going to have a dy to go along with that. So our variable force is what we just wrote down. That's our 62.4 times pi times our negative 1/3 y plus 4 squared. Let's see, what am I missing there? Times the distance. What is the distance that I'm moving my water? Anybody remember from the picture here? Y, yeah, that's this guy right here. I'm moving each chunk of water y. All right, so then I got a times y there, dy. And we're moving this stuff as y goes from, so we're assuming that the tank was full and we're pumping that water out off the top there. So we're going from y equals 0 to y equals 8 is what we're doing, because I only want to take off the top 8 feet of water. All right, we did the hard part. We set up the integral based on a couple of physics concepts. The physics concepts were force, which is weight, and then work, which is force times distance. So now you get the fun part of finding an antiderivative if it exists here. Now this is just kind of a polynomial with funky coefficients, so it should exist. So clean that up to the best of your ability. I'm going to do it at the same time, and then hopefully we'll get an answer that'll match in a moment. 9, 10, 11, 12. All right, I think I got something I can plug into my calculator. Just cleaning up the 8 cubed stuff. I think I have 620, no, sorry, 62.4 pi. And then that constant stuff cleans up to an 8 cubed over 3. What does that work out to be? If I didn't make a mistake anywhere. After doing it 3 times, I'm pretty sure I didn't make a mistake. 62.4 times pi times 8 to the 3rd divided by 3. I think what I got, 33,457-ish. Anyone else getting that? Yeah, so as far as this goes, it's, it's worth it to practice, cleaning up stuff like this to the best of your ability. This blue point right here would be a good point to whip out a calculator and get an approximation. Keep cleaning it up and hope that the blue approximation matches like this cleaned up version here. Right? I always double check my stuff numerically at different points in the calculation. Oof, that was exciting. So work, what would work be measured in here? So just to double check that, work is equal to force times distance. In our American system of measurement, we are measuring force here in pounds times foot. So the answer work is in foot-pounds is what that's measured in. If we did this in the metric system, we'd be using joules for work, I believe. Where's my notebook? All right, so I should label this as foot-pounds. So what do we say? It's approximately 33,467 to the nearest foot-pound. I get that right? Yes, no, maybe? Did I mess up a digit somewhere? 57, not 67. Oh, yeah, it was 56 point something. Yes, thank you. All right, let's try another one like this. Let's see if there was something interesting in the homework. Let's just bring up the homework. Actually, yeah, sure. Actually, I have a bunch of problems written down. Let's look at them instead. Where did I put them? Math, Parker, section 6.5. Okay, so let's see. There's some weight density stuff. Ooh, this is a good one. The force it takes to compress a spring. I don't know if anyone ever here ride public transit, if a train kind of thing. Did you ever look at the springs and the connectors for those trains? They're massive. Do you ever look at the springs in your car suspension? Right, they're pretty massive too. What kind of forces does it take to compress one of those? So we'll take a look at that. We just did a problem like number 5 here. And there's and this is from your book. Example 5 is just like what we did here. There's an example in the book. They do water. No, what did they do in their book? Oil, maybe? There's another one here where they say, okay, now do it with milk. Same problem, different constant. Right? Just practice setting it up. Let's try the subway. New page. And okay, so we got the force. It takes a force of 21,714 pounds So that's like 4 Honda Accords stacked on top of each other to compress a coil spring assembly on a New York City Transit Authority subway car from its free height, so when it's unimpeded by anything, of 8 inches, fully compressed, it goes down to 5 inches. Okay, so that's a lot of force. So we want to see what is the force constant for this assembly here. So that involves what's called Hooke's law. And I can't remember, did I mention Hooke's law last week? No? Do you guys ever read about Hooke before? You know who Hooke is? Not Captain Hooke, right? Totally different guy. I'll tell you a little about Hooke. Hooke was around kind of the same time as Isaac Newton. And in that day, people were a little bit more prejudiced, I think, than they are today, which kind of sounds hard to believe, but it's true. And Newton was known as a scientist, right? Hooke was known as a mechanic, right? And when scientists said mechanic, they were putting you down. Okay, but Hooke was actually a brilliant, brilliant guy. He was hard to get along with, but he was very smart, and he made a lot of amazing discoveries in that time. A lot of those contributions were to physics, calculus, engineering, architecture. He did a lot of amazing stuff. But he and Newton were not the best of buds, unfortunately. If they were, I think more amazing things would have happened in that time, but a lot of amazing things happened then anyway. But what he discovered is that when you have a spring, that's my best spring, that spring could be compressed, right? Or that spring could be stretched from whatever its natural state is. And what Hooke discovered experimentally was that the force that it takes to compress or stretch the string is proportional within reason to the distance that you try to displace its natural state. Okay, so you've got this nice proportional system that goes on. What that means is when we mess with springs, it is not like pushing a box along a flat ground. The force changes as you try to stretch it more or compress it more. The spring is resisting you more and more, is what this tells us. So we can't just use arithmetic to solve these problems. We have to use calculus if we want to find the work done when we do something like that. And here they're telling us that the force needed to compress the spring a certain distance is what? 21,714 pounds. And that every particular spring has a natural constant, kind of like a friction coefficient if you've ever messed with those before. And you can discover it by just measuring the spring a few times. Let's see, the distance that we tried to compress it here with this weight up there, we went from 8 inches, compressed it down to 5. So we pushed the spring a distance of 3 inches. So our constant must be our 21,714 divided by 3. And let's see, does 3 go into that? It does. So we got what? 3 and then 2 and then 7. Oh, did I make a mistake? 3, 2, 3. No. All right. Thought I could. Oh, 3 goes into 21 7 times. I knew that. I don't know why I wrote that. 7 times. 3 goes into 7 twice. 3 goes into 11 3 times. And 3 goes into 24 6 times. Is that right? 8, 24, 8 times, right. Oh gosh, my arithmetic is horrible today. Hopefully my physics and calculus stay better than my arithmetic. Maybe that was the problem earlier, Darren. Maybe my arithmetic was the problem. Okay, so that is our springs constant. Okay, so what do we know right now? We know that the force needed to move this spring is going to be 7238 times the distance. Did I get that right? Whew, okay. So that's the force. We also know that work is equal to force times distance. And if that force is variable, if it depends on something, then we have to integrate to get the work. Okay. So for us, work is going to be the integral. And let's say we're going to use the variable x. And I think they said they wanted us to move it 1/2 inch. Let me double check. We got part A, part B. How much work does it take to compress the first 1/2 inch, and then how much for the second half of it, 1/2 inch? Okay. So from 0 to 1/2 of our force, which is 7, 2, 3, 8, times the distance x. Okay. So that's this right here is my F. Work says you need to multiply that force by the distance, which is another x, dx. Everybody see where I'm coming up with those two different x's from? One comes from the force due to Hooke's law for springs. The other comes from the definition of work. Okay. Not too bad. We can easily do that. So we're just going to pull out our constant of 7,238. That leaves us with this right here as an x squared, antiderivative for x squared, x cubed over 3. And we are integrating that from 0 to 1/2. So that should give me 7,238 times 1/2 cubed over 3. And you make it a number on that sucker. (3619 over 12). And let's see, to the nearest whole number, 302. Anybody else getting that? Yeah. And then the measurement here, we're pushing it by inches. So this wouldn't be work in foot pounds. It would be work in inch pounds. So for the first 1/2 inch, it only takes 302 pounds. It's not too bad. We could get a really big guy to push that a little bit. You know, can I lift 302 pounds? I don't think I can. No, I'm pretty sure I cannot. I don't think I could lift 300 over my head. I don't lift weights anymore, but I'm pretty sure that's never been in my weight range. All right. Then they also wanted to say, okay, what about the second 1/2 inch? Is it about the same amount of work, or is it going to be more amount of work? Well, we know that according to this formula right there, it should be more work for the next 1/2 inch. That's what that formula up there tells us. Let's figure out how much more. So we're going to calculate some more work. And this time we're going to integrate as x goes from 1/2 to 1, right? The second 1/2 inch. And our formula was for that 7,238 x squared dx. We already know that antiderivative, 7,238 x cubed over 3 as x goes from 1/2 to 1. Okay, so, well, we know the first part, that's just 7,238 times 1/3 minus, well, that would be our previous answer of about 302, right? 7,238 times 1/2 squared over 3. Yeah, that's our previous answer. Yeah, so pretty much we have approximately this number right here, this right here, that would be the work it takes to move it 1 inch minus the work it takes to do a 1/2 inch. Oh, that should be a cube. Thank you. So, I messed up my board. What do we get approximately there? 200111. Anybody else get a similar answer? Yeah. And that's for the difference, right? This entire computation here? Okay. So it's approximately 2,111 inch-pounds. Okay. Way more work for that second half an inch. Whew. First half an inch was about 302 inch-pounds. Next, it's about 2,111. A lot more work. If we wanted to move it a whole nother inch beyond this, yeah, it would be plugging in 2 here minus this number right here. Yeah. Yeah, so I'm kind of curious, or even if we go the next half inch, it should be much more than that right there. So I'm kind of curious as to what's going to happen there. I'm going to plug it into, and actually, you know what? We have a, now we got to move on to other problems. We could play with this one all day, but yeah, so what we're going to find is every half an inch, it gets more and more and more work to keep compressing that. It's going to keep resisting us more and more and more every time we push on it. Okay, let's see. I promised, where is that problem? There's a lot of cool problems here. The hardest thing on all these problems is the setup. Okay, I promised Darren we would look at number 12 again. So let me grab the text and the picture. New page. Number 12 from the homework. And the picture. Screenshot that. Oh, why didn't that work? Screenshot. There we go. Okay, so now I haven't talked about pressure yet, so I just want to take a quick peek at what the book says about pressure. Zoom out a touch. Okay, so fluid forces, let's let you go away and you go away. There we go. And can I scroll here? Oh, good, I can scroll. So just something to consider from this cross section right here. It doesn't matter whether this was a pool in someone's backyard or like Mackay Dam or the ocean. Okay. All that matters is how deep the water is, not how far out it goes in terms of the force, if the water is still. Now let's not throw waves into the picture here. That's a whole nother problem. So that's something to consider. Other thing to consider, oops, back here, is that the pressure at a depth 8 is related to the fluid's weight density, which we've been talking about weight density in terms of pumping. We're just going to look at it in a slightly different way, times the height. Okay. All right, so that helps. Now, if it's a uniform cross section of this wall all the way down, like it's always this rectangular piece of wall, that's just arithmetic to figure that problem out. It becomes not arithmetic when you have a cross-sectional area that's not just a rectangle, like this triangle. Okay, so if we consider any rectangular chunk cut horizontally about this, that's going to be a different chunk there than it is up there. Okay. So now what happens is the pressure becomes variable as I move from the bottom to the top here, because the width is variable as I go from bottom to top. Okay. And so we're going to need calculus to do a little integration on that. Other things we need to know here are that the force is just going to be the pressure times the area. Okay. And that's just going to be the weight density times the height times the area based on the previous one. So the things we need to know: what is the cross-sectional area of the thing the water is touching, or whatever the fluid is? What is how much water is above, or whatever fluid is above that point, right? The height from the surface, and then the weight density of whatever the fluid is. Because oil or salt water will put more pressure than regular water. Okay. Or what do we think about alcohol? Will that put more or less pressure than water? Less, because alcohol is lighter than water, right? Now, how about air? Way less, right? Okay, but air does exert some pressure on things, okay? And it exerts equal pressure all the way around, which is, why bubbles form a sphere. Do you guys ever talk about that in physics? Those of you who had physics, why bubbles form a sphere? And it just has to do with equal pressure all around, forces that shape. All right, so this is all we need to know to do the problem, and then we need a little bit of geometry to work with it. Okay, so the point of that discussion right there is it doesn't matter how long the tank is. It could be 1,000 feet long, and that's not going to change anything in this problem. So that 30 feet in terms of pressure is irrelevant. All that matters is the cross-sectional area on the side here that we're looking at, and we're looking at that side, and the depth of the water. Okay, how much water we have there. Okay, so let's see. The end plates, these triangular things of the trough shown here, were designed to withstand a fluid force of 6,667 pounds. Okay, so pounds, again, is the measure of force in our weird American system. What is it in the rest of the world? Does anybody know? Newtons is the common measure, which is kilograms times meters per second squared. Right, it's kilograms with gravity. How many cubic feet of water can the tank hold without exceeding this right there? And again, we're not concerned about the weight of all the water. We're just concerned about the pressure weight on the wall, the side wall here, just this triangular plate. All right, so let's play around with this, see what we can figure out. I need a pen. Pen, where are you? Okay. And so just a reminder about the, what letter did they use here? They used F, yeah, force. The force that we're concerned about is going to be equal to the weight density of the fluid, and I think we just have water here, times the height of the water involved, times the cross-sectional area. And here, our cross-sectional area is going to vary as we move from the bottom to the top of this figure. So here they're recommending a coordinate system. And so what we need to consider is what is the equation of that line right there to start figuring this out. So here it looks like y is equal to a rise of 10 and a run of 4 times x. And there is no, the y-intercept is 0, right? We need to know for a triangle like this, a cross-sectional rectangle. So that's going to be what we're calling A up here as we set this up. We just calculated the distance from here to there. What I want is the distance all the way across that right there. So I need to rewrite this equation as x equals. So let's see, 10 fourths is what, 5 halves. Flip it and I get 2/5 y. That gets me halfway across because that's the x value. To get all the way across, I'm going to have to double that. So my rectangle right here is going to be 2 times that, so 4/5 y. And then for calculus, we're going to say it's delta y thick. So that's my cross-sectional area there. Yeah, that's right. So at any particular height from here to here, this tells me how wide my rectangle is total, and that's the thickness of my rectangle. My depth is going to be the y, or my height here. So I think a chunk of force for this situation is going to be the weight density of water, 62.4, times the height of that rectangle. It is y up from the bottom, times the cross-sectional area, which is 4/5 y dy. So to get the total force exerted, then we're going to have to integrate as we go from 0 and let's say to some depth d. that thing right there. So the 62.4 is hanging out, the 4/5 is hanging out, and we have a y squared dy. And what's the unit of force in our system here? Pounds, right? So this is going to give us an amount of pounds, is what we were just calculating here. That's the unit of force we're messing with at the moment. Okay, that's not too bad to clean up, right? So we have total force. Let's switch colors. What am I doing on time? We gotta hurry this up. Total force is equal to that 62.4 times 4/5. Oops. Times, let's say we had a y squared, so y cubed over 3 is our antiderivative for that part, from 0 to d. So the total force is a function of the depth. That should make sense, right, when I look back at my picture here. More depth, more force. Okay, so that's going to give us, I guess we can clean, does anyone clean that constant up right there? 49.2, okay, so 49.92? 49.92, got it? And does that include the 3 or not? Not including the 3, okay. All right, so d cubed, and that's, let's see, dividing by 3 is probably not going to be nice there. Oh no, 3 goes into it nicely, yeah. What did you say, 16.64? 16.64 d cubed. Okay, so that's the force. Now, we can't let the force exceed 6,667 pounds. So if we set that equal to, come on, there we go. 6,667 pounds, that will tell us what the depth we can get away with is. And then the catch here is, the catch on the online homework is this question right here. How many cubic feet of water can the tank hold? So we're just about to calculate the height. Then we have to take that height and figure out what the volume of the tank with 30 feet wide is. So give this one a shot on the homework tonight. I'll finish this particular problem tomorrow. All that's left to do is once I discover D, then I need to figure out what's the volume for that particular D. And those are the two answers that we're trying to accomplish here. What's the depth? Based on that depth, what's the volume? Boom, done. All right. So we'll come back to this one tomorrow. So tomorrow is we're going to review. We'll look at another force problem tomorrow. We'll look at another pumping problem, and then we'll do some volumes, which tend to be the hardest thing we've done so far. Don't forget to look at that practice test tonight. And by the way, the quiz is just like 2 of the problems that we did today. You haven't done the 6.4 quiz? You should do that soon. Yeah, if you haven't done the quizzes, please do the quizzes before the test. You need help on one of those? Sure. It's also just set up. Yep, it's always set up.